In this lecture, we will study the topic power factor correction or improving power factor. We already know that for loads, most loads are inductive. This means they have lagging power factor, and as the amount of inductance increases, as we discussed in last lecture, power factor goes down. It should ideally be 1, but it goes down. So we need ways to improve it and to bring it closer to 1. Right. One such technique is that we introduce a capacitor, and we know that a capacitor introduces a negative Q. In last lectures, we have studied that in a power triangle, we have this P, this Q, and this S. So this Q is positive because the load is inductive. So the idea is to decrease this vector, we introduce some amount in the negative in its opposite direction by introducing an element that adds a negative Q, and we all know that capacitors add negative Q. So this plus this means the magnitudes are subtracted and the net Q would be smaller, maybe of this size, and we have net Q smaller, means net inductance is smaller, and we have the new theta, which has a larger power factor compared to this greater theta. So we have a smaller theta after we introduce Q capacitor. We have a smaller theta. Smaller theta means larger power factor. This is a small recap from the last lecture. In this lecture, we'll see how can we improve the power factor of a given load. This is the load given, and whose power is 50 kilowatt or 50,000 watt. The power factor is lagging and is 0.8. This means this is an inductive load. And the RMS voltage drop across load is 220 at an angle of 0. And we are working in a 60 Hertz system. Right. So what we are required to do is we need to find the capacitor, so that after adding the capacitor, the new power factor is improved from 0.8 to 0.95. So we need to find the value of this capacitor in the end. This is the task, so that the new power factor is improved and it is now closer to 1. So let's draw the power triangle of the system that we have without adding this capacitor. First draw the power triangle for this load. Right. And we call it old. This means we have yet not added the capacitor. This theta can be computed, and this theta is theta old. We can compute it by computing inverse cosecant of the power factor given. The power factor is 0.8. We know that cosecant of this theta is the power factor we studied in last lecture. So the old theta comes out to be 36.8. Let's see what is Q old then. Since this is a right angle triangle and perpendicular over base is tangent of this theta. So we use this identity that perpendicular of a right angle triangle divided by its base is equal to the tangent of the theta. So we put theta, we have just calculated 36.8 here, and we see that Q old comes out to be 37,500 var. We know the units of Q, the reactive power, is var. Since and we don't need to compute S old, so now we have P old, and P old remains P new. It remains the same. because adding a capacitor doesn't affect P. We know that P, the average power absorbed in capacitors and inductors, is 0. So adding a capacitor in parallel doesn't change P of the load, the average power. So after we have computed this old Q and old P is already known, and we have computed this theta, we are now ready to compute new theta given the new power factor. The desired new power factor is 0.95. So in this means 0.95 is cosecant of this new theta, and the new theta would be computed by computing inverse cosecant of this new power factor, which comes out to be 18.19. So this diagram shows both thetas. This is the older theta we have, which is 36.8. This smaller theta is the new theta, 18.19. This is the older theta, and this is, since this is the new theta, so this is the new Q, the net. This is the new Q that we want. So Q net should be this whole Q that we had previously without adding capacitor, minus this much Q. This Q should be provided by the capacitor, this one. So this Q capacitor is negative, so we want to reduce this Q by this much amount. So this means we have to add a capacitor that introduces this much Q net. So given this P new, we can use the same formula that we used here to compute Q old, which is P times tangent of theta. We can use the same formula for this new theta and compute the new Q. 16,430 var is the new Q. This is our new Q, this one. So this net Q that is reduced from this older Q is the one provided by the capacitor. So let's compute the difference of this whole Q minus the Q that we want to subtract. So Q old minus Q new, Q net, and this is the Q, the reactive power that we want our capacitor to provide. And since it will be negative, it will be subtracted from this whole perpendicular, and the new perpendicular will be smaller in magnitude. Right, so this much is the Q that should be provided by this newly added capacitor. And we know that both P and Q can be written as V squared over Z, or they can be written as V times I, because this Q can be written as for a capacitor because the other term sign gives always a 1, because the current and voltage are 90 degrees, therefore the sine term is always 1, like the cos term is always 1 in case of resistors. So this sine term that we write here is Vi sine of theta V minus theta I is always a 1, because they are at 90 degrees and sine of 90 is a 1. So for inductors and capacitor, this sine term for Q always gives us a 1, and the cos term in case of P always gives a 1 for resistive loads. So this Vi can also be written as V squared over C, and it can also be written as I squared times C. So we write it V squared over C, and we know that Z for a capacitor is 1 over j omega C. Since we are working with the magnitudes, 1 over omega C. So the magnitude of Q capacitor is this term will come into the numerator finally, because this is in the numerator and is numerator denominator over denominator. So this comes in the numerator, omega C V squared And now we have Q capacitor, which is equal to the net Q that we want to reduce, is equal to, is omega is 2 pi f. And in the beginning we are given that we are working with a 60 hertz system. We are given that we are working in a 60 hertz system. So we put a 60 here, times C time the input voltage is 220 at an angle of 0. This means 220. So in this equation we have only one equation and one variable. So C comes out to be this much. The students are required to solve one or two different problems related to power factor correction or improving power factor, and they are also required to do some practice for the midterm exam. Right. This is all for today's lecture. Thank you.